Hello everyone, welcome to the channel Statistica Hub. So we are doing the rank concept. Okay, now in rank concept there is a very important thing which is called the null space and nullity. Null space and nullity. Okay, and in that, what is actually nullity? That nullity is the number of vectors present in the null space of a matrix. Okay, what is nullity? Nullity is number of vectors present in null space of a matrix. Okay, this is my nullity, or you can also say that the nullity is basically the dimension of the null space of the matrix. Okay, you can also define it as the dimension of null space of matrix, let's say A, of matrix A, and this is also called the nullity of the A. Okay, now the number of linear relations among the attributes is given by the size of the null space. Okay, so what is actually null space? Null space is null space. Okay, let's say I have the transformation, linear transformation, which is going from transformation x to ax. Okay, this is my linear transformation. Okay, and I have this matrix A of m cross n. Okay, and the null space of A, null space of A is defined as the NA. This is how we denote a null space of matrix A. Okay, the null space of A is actually all the values, those values of x for which ax is equals to 0. Okay, what is this? That means you can also say it like this, that this is the corresponding solutions of the homogeneous equations. Okay, I want to find the solutions of the homogeneous equations, and for that those solutions are my null space of the matrix. Okay, now this null space n of A is constitutes a vector space. Okay, because in the linear transformation we have seen this, that the solution of the homogeneous system, solution of, okay, this is the solution of homogeneous system constitute a vector space. It forms a vector space. Okay, now let's just see it like this, that my matrix A, let's just write it like alpha 1, alpha 2 to alpha m. Okay, this is my matrix A. Okay, and I want to find the null space of A. Then I can write it as Ax is equals to 0, where x is my row vector. X is any row vector. So if I multiply this A to the row vector x, okay, then I would get something like alpha 1 dash x, alpha 2 dash x to alpha m dash x. Okay, and that will be equals to 0 0 0 0 0. Okay, so from this you can see that x is orthogonal to any row of A. Okay, this vector x is orthogonal to any row of A by the property of dot product. You can see from by the property of the dot product here. Okay, any row of A, any row of this matrix, because they have this type of matrix where the solutions as like Ax is equals to 0. Okay, now this Na is called the null space. This is called the null space. Okay, now I am writing VRA, which is my row space. Actually, let's write it as RA. I am using this only for the whole lectures, so let's write it RA. RA is my row space, and these together form the orthogonal spaces. These are actually the orthogonal spaces, that Na and my row space of A, null space and row space, are actually orthogonal spaces, or these are orthogonal spaces. That means that these null space are perpendicular to the row space of A. Okay, Okay, why are we saying this? I think you got it. Okay, by the property of the orthogonality, sorry, not the orthogonality, by the property of the dot product of the vectors that we have done in the linear transformation topic. Okay, by using that, we can say that if we have a matrix A and we multiply that matrix to x and we want to find the solutions of these x's vectors, then that means Ax equals to 0. Okay, now what is my null space? Null space is actually the solutions of these homogeneous system of equations for which my solution is 0. That means for all those value which has Ax is equals to 0. Okay, this is my null space of the matrix. Okay, now these null space and the row space are orthogonal spaces, are actually orthogonal spaces. Okay, so if we say that the rank, if we say that rank is equals to r here, okay, the rank is equals to r, that is we have the dimension of row space of A is equals to r. Okay, that's what we mean. If we have rank is equals to r, we can write it down as the dimension of the row space of A. This is what our rank is. Okay, now what is the dimension of null space of A? The dimension of null space of A is basically n minus r. N minus r. Okay, this is n minus r. You can this is dimension of null space of A is basically the nullity of A. What? This is nullity of A, and it is denoted by like this. Okay, this is how we denote the nullity. And so I can write it down as nullity of A is equals to n minus r. Okay, and this is very important result. It is written as rank nullity theorem. This is my rank nullity theorem. Okay, so the rank nullity theorem helps us to relate the nullity of the data matrix of the rank and the number of attributes of the data. Okay, so the rank nullity theorem is actually can be written as rank nullity theorem. It is actually nullity of A plus rank of A, and that is equals to total number of attributes of A. Total number of attributes of A. That is total number of columns in A, or total number of that is total number of columns in A. Okay. So this is my rank nullity theorem. Okay, that we have null space of A. This is my null space of A. This is the rank of A, and they both together form the. If we add these two, then we would get the total number of attributes of this matrix A. This is my rank nullity theorem. Okay, now we can see use the rank nullity theorem like that. Say I have this matrix A, which is as 1, 2, 3, 2, 4, 6, 0, 0, 1. Okay, this is my matrix A. Okay, then what are the number of columns here? We can see that the number of columns in this matrix A are 3. Okay, I have number of columns here. Okay, let's just reduce it, this matrix to the echelon form. Okay, we'll reduce it like in R2 will apply R2 minus 2R1, and in R3 we'll apply R3 minus 3R1. Okay, and we would get 1 2 0, and this would be 0 0 0, and this would be 0 um 3 2 just 6. Okay, 0, and this is 1 minus 3 minus 2. Okay, let's just change these in interchange these rows. Then we would get 1 2 0 0 0 minus 2 0 0 0. Okay, so this is the echelon form here. Okay, I have gotten my echelon form. Okay, now you can see that if we see this matrix, then we can see that r1 and r3 are linearly independent. Okay, and in this, as we have exchanged the rows here, so in this r1 and r2 are the linearly independent rows here. Okay, then the rank of this matrix, which is the number of non-zero rows in its echelon, we have this rank of this matrix A as 2. Okay, this is the rank of this matrix. Okay, now if I want to find the null space of this matrix, okay, then what will we do? We will apply Ax is equals to 0. Okay, so let's just use the echelon form here. Okay, that will be easy for calculating purpose. 1 0 0 2 0 0 0 minus 2 0. Okay, and my x would be like x1 x2 x3, that is equals to 0. This is vector 0. Okay, so what are the corresponding equations here? That is x1 plus 2x2 is equals to 0, and minus of 2x2, sorry, minus of 2x3 equals to 0. So I would get x3 that is equals to 0, and we would get x1 equals to minus of 2x2. Okay, so the null vector here, let's say b is my null vector, which is, sorry, x is my null vector here. So x1 x2 x3, I can write this. What is the value of x1? X1 is actually minus of 2x2, x2 is x2, and x3 is 0. Okay, that is, I have this null vector as minus 2 1 0. This is my null vector. Okay, and the number of parameters in the general solution is the dimension of the null space. Okay, so what is the dimension of this null space? We have the dimension of this null space as 1, because we have one vector here. Okay, and we have the rank of A as 2. So by the rank nullity theorem, we can easily check this, as I have rank of A is equals to 2, that the rank of A plus nullity of A is equal to the total number of attributes. We have total number of attributes, that is total number of columns as 3. So that is equals to 3. So we have null space of A as 1, and row, sorry, rank of the A as 2. So that is 1 plus 2 is equals to 3. So it is satisfying the condition. So that's how we can use the rank nullity theorem, and that is very important topic actually. You have to use it in many ways. Okay, so there are some results in this null space and nullity that are like this. That first result is that null space of A is perpendicular to row space of A. Okay, we have seen that how it is satisfied, and the rank of A into A's transpose is equals to rank of A, and that is equals to rank of A transpose, and that is equals to rank of A transpose. Okay, okay, and third result is, you can check that. Okay, and third result is that if we have a of m cross n, this is not actually a result, this is for just general purpose, that if we have a of m cross n, okay, then what is m? M is actually rank of A, that is the row nullity of matrix. M is what? Row nullity of matrix A. Okay, and n is n minus rank of A, that is the n is rank of A, that is column nullity of rank of matrix A. This is m minus rank of A, and this is n minus rank of A. This is what? By the help of rank nullity theorem, that is rank of A plus null space of A, that is equals to total number of attributes. Okay, and that depends on the, we are on which attribute we are taking. We are taking number of rows, we are taking number of columns, that is m or n. Okay, so we are writing this on the on that perspective. We have nullity of A, that would be equals to m minus rank of A, that means row nullity of matrix A, and if we take number of columns, then nullity of A would be as n minus rank of A by applying rank nullity theorem, and this is said to be the column nullity of matrix A. Okay, so this is the concept of rank nullity theorem. Okay, now we will see a very important concept in the ranks, which is, we have done this, that the upper bound for rank of AB. What is the upper bound for rank of AB? We have seen this in the earlier lecture, that the upper bound for rank of AB is actually the minimum of rank of A, comma, rank of B. Okay. Now, how do we get this result? And what does it truly means? Okay. What does this result shows us? Okay, so for that, let's just consider that I have two matrices A and B. I have these two matrices. Okay, and I am considering the first case that these two matrices have same number of rows, same number of rows, and the second case is that I am considering that these have same number of columns, same number of columns. Okay, these are my conditions here for these matrices A and B. A and B when they have same number of rows, and A and B when they have same number of columns. Okay, now B is, if B is equals to AC, if and only if B is equals to AC, that means the column space of B is a subset of column space of A. Okay, let's see it how can I write this. Okay, so as we have seen that we have given the condition that they have same number of rows. Okay, so if let's say I have this matrix A of m cross n. Okay, and I have here m rows. Okay, so I have to as B have also m rows, so I would write here like this. Okay, m. So what is the C matrix here? C would be of n cross m. C would be of n cross m, and the corresponding multiplication of these two matrices of m cross m. Okay, so if we have look at like this, then by the concept of inverses, this is actually my right inverse. This is my right inverse of matrix A. Right inverse of matrix A. So if we have same number of rows, we have same number of rows. Okay, so B will be of m cross m, and A will be of m cross n. M cross n. Okay, so as they have same number of rows, so we can say that from here we can say that the column space of B would be subset of column space of A. Okay, if they have same number of rows, this is the required condition for that. Okay, similarly here, if we have same number of columns, okay, and if and only if B is equals to DA, this is what, this is the left inverse, this is left inverse. Okay, this is left inverse. So as they have same number of columns, A would be of m cross n. Okay, and the corresponding B will be of n cross m. Okay, and B will be of n cross n. Okay, so B will be of n cross n, and from this, as they have same number of columns, we can write that the row space of this B would be subset of row space of A if I have condition B is equals to DA. Okay, so this is my, these are actually very important results. Okay, this is the concept of, we are using the concept of left inverse and right inverse for checking the condition here for the upper bound for rank of AB. Okay, so we have written this, that the rank of AB is less than equals to minimum of rank of A and rank of B. Okay, so if we multiply AB, we are multiplying A into B. Okay, that means we are writing this is the matrix A into B. That means this is my this is my result AB, and I am multiplying A, this is A, and this is B matrix, and this is the corresponding multiplication of these two matrices, that is AB. Okay, now this is actually single matrix. I am taking this as a single matrix here. Okay, now if you look at like this, by using the concept of if they have same number of rows, okay, what will be the case here? If they have same number of rows, that means that the column space of AB would be subset of column space of A by the first rule. Okay, because we have, if we have B is equals to AC, if we have B is equals to AC, then we say that column space of B is subset of column space of A. Now similarly applying it here, we are saying that the column space of AB is subset of column space of A. Okay, now if we take the dimensions of these, then I can write it as that the rank of AB is less than equals to rank of A. Okay, this is my first equation. Okay, now by the second result, we have this second result, which is the left inverse result, that if and only if we have the condition that B is equals to DA, that means that the row space of B is subset of row space of A. Okay, so by using this concept, I can write it for this equation as that the row space of AB is a subset of row space of B. Okay, that means rank of AB, by taking the dimensions of the row space, that means the rank of AB is less than equals to rank of B. Okay, so these are my corresponding two equations here. Okay, so if we add these two equations by taking these two results into account, we got that this result implies that rank of AB is basically less than equals to minimum of rank of A comma rank of B. Okay, so this is the basic concept here behind this result of the upper bound of rank of AB. Okay, now this rank of AB, this let's just see it here. This rank of AB is equals to rank of B if we have A is of full column rank. If we have A is of full column rank. Okay, so by the theorem, what we have? By the theorem that is of, like, I'm talking about this. By the theorem, we have that the rank of AB is actually less than equals to rank of B. Okay, if we are taking of the rank of B into account only, then because of A is of full column rank. Okay, so rank of AB is less than equals to rank of B. Okay, and we are saying that A is of full column rank. Okay, that means it has a left inverse X. What is that? It has a left inverse. Let's say that inverse is X. Okay, because you can see there that if we are talking about the number of columns, if we have same number of columns, we are talking about the column rank. If we are talking about the column rank, then we are talking about actually the left inverse. Okay, so if we have A is of full column rank, then it means we have a left inverse X. Okay, so I can write it as X A is equals to I. Okay, this is how we can write the left inverse. Okay, then if I want to write it as that rank of B, I can write it as rank of identity of B. Okay, by multiplying the identity in this matrix, it doesn't cause any effect. Okay, now this identity I can replace it by XAB. Okay, now this XAB is actually the multiplication of XAB, that is AB into X. Okay, and by using the property of the left inverse, I can write it as that rank of XAB is less than equals to rank of AB, because row space of XAB is subset of row space of AB. Okay, like previously we have done just here. Okay, so by using this, I am saying that rank of XAB is less than equals to rank of AB. Okay, so from this we can see the equality here, that I am saying here that rank of AB is less than equals to rank of B. Okay, and here we are saying that rank of B is less than equals to rank of AB. Okay, so by these two equations, as these X is equals to identity, I can write it as rank of B. Okay, so by these two things, by these two statements, we got that rank of AB is equals to rank of B. Okay, we have got the equality here. Okay, now similarly, we can write it down as rank of AB is equals to rank of A. If B is of full column rank, sorry, full row rank. If B is of full row rank, then we will have rank of AB is equals to rank of A. Now you can check it similarly like the previous one, as we have checked for the A. If A is of full column rank, you can check it for that. Okay. Now let's just see the lower bound. What? Lower bound for rank of AB. Okay. So in the lower bound concept, we have seen this. We are using the Sylvester's inequality. Sylvester's inequality. The lower bound is actually the Sylvester's inequality, and in that we are taking if A is of m cross n and B is of n cross p. Okay, then the rank of AB is greater than equals to rank of A plus rank of B minus n. Okay, this is my Sylvester's inequality, and the equality in this equation holds. The equality holds if we have, if and only if we have null space of A is subset of column space of B. Okay, if we have null space of A, and that will be subset of column space of B. This is the equality condition here. Okay, now this Sylvester's inequality can also be stated as like this, that the nullity of AB is less than equals to nullity of A plus nullity of B. Okay, now if you look the nullity of AB, what is nullity of AB? Nullity of AB is equals to P minus rank of AB. By the rank nullity theorem, I can write it as that nullity of AB is basically P minus rank of AB. Okay, here what I am taking? What I am taking is actually if we take AB, that would be equals to M cross P. M cross P. Okay, I am taking into account the number of columns here. Okay, so P minus rank of AB. That's why I have written P here. Okay, so nullity of AB that will is equals to P minus rank of AB. Now, if we look the nullity of A, what is the nullity of A? Nullity of A is N minus rank of A. Similarly, the nullity of B is equals to P minus rank of B. Okay, so as we have rank of AB less than equals to rank of B, that means so we will have nullity of AB is greater than equals to nullity of B. Okay, you can check it here by these conditions that I have nullity of AB. If you will put these values, that nullity of AB. Okay, I am saying that rank of AB is less than equals to rank of B. Okay, by the upper bound theorem. Okay, by the upper bound theorem. Then what is the rank of AB? Rank of AB is actually P minus nullity of AB. Okay, and rank of B is actually P minus nullity of B. Okay, by cutting this down, I can write it as that the rank of B is less than equals to rank nullity of AB. Nullity of B is less than equals to nullity of AB. Okay, so this is what I have got. Okay, so if we have A and B as the square matrices, okay, A and B as square matrices, okay, of same order, of same order, then we will have nullity of AB less than equals to nullity of A plus nullity of B. You can check it very easily. Okay, because in that case, if we have A and B of same order, and let's say of n order, okay, then in that case, this P, these all will like n minus rank of AB, n minus rank of A, n minus rank of B, and you can easily check that nullity of AB in that case is less than equals to nullity of A plus nullity of B. Okay, so from this we got a very important result of the rank nullity 2, that maximum of nullity of A comma nullity of B is less than equals to nullity of AB, and that is less than equals to nullity of A plus nullity of B, and this is said to be the Sylvester's law of nullity. Okay, this is my Sylvester's law of nullity. Okay, now there is one more, which is Frobenius inequality. In this inequality, we have three matrices. Let's say A, B, and C. These are my three matrices, and in this we say that rank of A, B, C is greater than equals to rank of AB plus rank of BC minus rank of B. Okay, this is my Sylvester's inequality. Okay, now there is an concept of rank factorization theorem. Okay, so what does rank factorization theorem says? It says that every non-null matrix can be written as a product of two full rank matrices. Okay, every non-null matrix can be written as product of two full rank matrices. Okay, so if I have a matrix which is of m cross n and with rank r greater than equals to 1, I'm just saying, giving the statement, I don't know what is the rank of this A, but I'm just saying that the rank of this matrix A is r, which is greater than equals to 1. Okay, then I have these two matrices, that is P comma Q is my corresponding matrix, are corresponding two matrices, and this is said to be a rank factorization of A. Okay, if P is of M cross R and Q is of R cross N and A is equals to PQ. Okay, in that case, we can say that P and Q are the rank factorization of A. Okay, so there is one thing too, that if P comma Q is rank factorization of A, then Q transpose P transpose are the rank factorization for A transpose. You can easily find that by this property. Okay, so now just see an example of this rank factorization theorem. So let's see that if I have this matrix A, which is 1 2 1 1 3 7 5 2 1 3 3 0 4 9 1 8. Okay, this is my matrix A. Okay, so now just let's reduce this to the echelon form. So for that, let's apply in R2, which is R2 minus 2R1. In R3, we'll apply R3 minus R1. And in R4, we'll apply R4 minus R1. Okay. So by this, we will get 1, 3, 1, 4. And this would be 0, 1, 1, 1, 0, 2, 2, minus 3, 0, minus 1, minus 1, 4. Okay. Okay, now let's just apply another transformation, that would be R3. In R3 we'll apply R3 minus 2R2, and then R4 we'll apply R4 plus R1 plus R2. Okay, so from this we will get 1 3 1 4 0 1 1 1, and this would be 0 0 0 minus 5, and this would be 0 0 0 5. Okay, now we will apply in R3, sorry, in R4. In R4, we will apply R4 plus R3. From this, we will just do it here. It would be 0. Okay, this would be 0 here, and then after this, we will apply. And okay, let's apply here like R3. On R3, we will apply R3 into minus 1 by 5. Okay, and this would do this one 1. Okay, this will element will be 1. Write this into the next matrix also. Okay, I'm just changing the elements here only. Okay, and now it will apply in R1 as R1 minus 3R2. We will get 1 0 minus 2 1 0 1 1 1 0 0 0 1 0 0 0 0. Okay, so now let's just make these two elements. It is actually canonical form, row canonical form. I am reducing this to the row reduced canonical form. Okay, now let's just apply the transformation here. In R2, we will apply R2 minus R1, and in R1, we will apply R2 minus R3. R1 minus R3. Okay, after this, we will got the matrix like 1 0 minus 2 0. Okay, and this would be 0 1 1 0 0 0 0 1 0 0 0 0. Okay, so I got my column as pivot elements like 1 1 1. These are my pivot columns. Okay, pivot elements, these are pivot elements. Okay, so for finding the P and Q matrices, that are the rank factorization for this matrix B, so from this you can see that the rank of this matrix also, the rank of this matrix is 3. Okay, the rank of this matrix is of 3. So P will be of 4 cross 3, and Q will be of 3 cross 4. Okay, Q will be of 3 cross 4. So what is P? P is obtained by removing third column of A, as it has no pivot. Okay, this column has no pivot, so we'll just remove this third column in this matrix, in this original matrix, and my P will be 1 2 1 1 3 7, sorry, 3 7 5 2 4 9 1 8. This is my P, and Q will be obtained by removing last row, as it has all the elements as zeros. Okay, so my P will be 1 0. This is taken from this echelon form, canonical form, which is 1 0 0 0 1 0 minus 2 1 0 and 0 0 1. Okay, this is my q. So q is of 3 cross 4 and p is of 4 cross 3. Okay, so if we multiply these two matrices, we would get our corresponding matrix A. So this is the rank factorization of the matrix A. Okay, into P and Q. This is how we can apply rank factorization. Okay, now the rank factorization, like this, I am writing this rank factorization as A is equals to PQ. This is my rank factorization of the matrix A. Okay, where we have taken the condition that R is greater than equals to rank of A. Okay, and we can say that R is the rank of A. R is equals to rank of A, and rank of P is equals to rank of Q, and that is equals to R. That means P is of full row rank and Q is of full P is of full column rank and Q is of full row rank. Okay, if they have equal ranks as R. Okay, and you can also see it in the form of basis too, that columns of P form a basis of column space of A, and the rows of Q form a basis of row space of A, of the matrix A. Okay, so this is the basic of the rank nullity theorem, that how can we apply it. This is a very actually important concept, that in the null space of the matrices we will apply this in the system of linear equations too. Okay. Okay, so this is all about this lecture. Thank you.